So it probably looks like there's a lot on the screen, and there really is. And I'll be making different parts of the screen smaller and larger. So we're just going to start on the top, and we're just going to build on this idea of what's really going on when you bond something. You know, we got kind of obsessed a few chapters back about electrons and how when you are looking at where they are in the atom, are they, you know, in this place, are they up, or they down, they phasing, what's their spin, all that craziness going on. Well, we still care about what those electrons are doing, but this is the very last bit of us obsessing over electrons in this chemistry course. After that, we're going to get into a lot more actually doing chemistry, plus formulas. So hang in there. This stuff may seem weird, and it's okay if you think it's weird, because it is kind of weird, because electrons are tiny and they don't act the way you expect them to act. So valence bond theory. So this is the beginning of like bonding and theories, and it was built upon by something called hybridization. So that's not like a brand new term. So it was built upon with hybridization. So this describes covalent bonds as overlap of the half-filled atomic orbitals. So that seems like a lot of a word. So remember we were talking a long time back about how the electrons, if the outer electrons could be in an s orbital, which we drew kind of like that, and it could have a total of 2. Or it could be in a p, and they might both be in the same lobe, or they might be in opposite lobes, but they had that kind of a shape with a p. So in this picture, we're using these like funny looking sphere things kind of for our pictures. And so a half-filled atomic orbital, it just is saying like if carbon is doing a bond with hydrogen, carbons come into the bond with 1 electron half-filled, because you can put 2 in an orbital, in its atomic s orbital. So the idea is that those 2 orbitals would overlap. Each of the half-filled orbitals contain 1 electron, and when they each overlap and they come together, then you have a pair of electrons that are what's shared, that's the covalent side of things, between the 2 bonded atoms. So just a reminder again, there's the shapes. We're going to be using this kind of a shape. And behind this theory is the idea that bonding requires a certain unique distance between 2 atoms. It allows for the lowest energy bonding. And let's look at what this distance is like over here. So on this chart, I know you're seeing a graph. It doesn't look like it's got any units. The red line at the highest point, that's high energy, and that's what you don't want. That's bad. The atoms don't like it. No one likes to be high energy. And then you can see there's a little spot where the ball is right now on the graph, and that's lowest. Like you can see it's a little lower than all of the other ones. That's the perfect bonding spot. That's what you want. And depending on the atoms, let me show you, like see it's a little deeper for some atoms. So some atoms it's better to be bonded. Look how deep oxygen is. And we know oxygen likes to form bonds with other oxygen atoms. But we know like neon and argon, not so, crazy about it. So anyways, as we do this, what I'm going to do is I'm going to pull these atoms apart. And you'll notice that if I pull them a little ways apart, the electrons are still going to notice the other nucleus and slide towards it. It kind of moves like that. And there actually is usually a little bit of movement like this. Now, if I pull it far enough away and I stop, those electrons on that right atom, it's not going to notice the nucleus on the left. Now, if you'll watch really slowly, look. Do you see how long it took for it to notice? But they are moving towards each other now, right? So I have to move it quite far for there to be no movement at all. See how far that is? So no interaction. So what happens if I get into that location and then I push them tighter together? So what I'm basically going to be doing is I'm going to be pushing it close enough so the nuclei, which are both positive, could repel. So you can see how it's going up. So that's bad. Now let me show you what happens when I release it, because they're too close. The nuclei pushes that away. It kind of overdoes all of the bonding. So you can pull up this simulation. It's linked, and you can see what happens if you take the different atoms and you try to put them closer or farther away. So it's really important that the atoms are the right distance apart, and that's unique to the atom. It's like atom specific for the distance it's going to be. And we call that distance between the 2 nuclei like the bond length. And then what you also need to know is it has to be oriented for the greatest overlap. Now, this doesn't matter as much for the s orbitals because they are both circular, so kind of like you can't mess up how you overlap circular things. So right here, like they're both circular. So that's, I mean, anywhere you put it, they're going to be overlapped, right? So this is a bigger issue when we're dealing with p orbitals. But what you need is the greatest overlap. And it's when they're oriented in such a way as they overlap on an axis between the two nuclei. So we just want to make sure that this bond is right between them. And you're going to see we've got some examples here in just a second. So the overlap direction is important. So if we're trying to do, and you'll learn that this overlap we're talking about is going to be called a single bond overlap. It's a sigma bond. Sigma bonds begin with being single bonds. You'll notice if this is the nucleus and this is the nucleus, and all this is where its electrons are, if they overlap with the picture on the left, this has a pretty good overlap. So that's going to be a good sigma, which is a single bond. And you'll notice how they're like directly between the nucleus. So that's really good. And then you'll notice here, like here's between the nucleus, and then like this space is not quite as large as this space. So that's not very good overlap. So this would be an example of when you have two P's overlapping. This is two S's. You can't get it wrong with two S's. And then this is what you want for an S and a P. You don't want this one right here. It might feel like it should go there, but you don't want it there. There's some phasing issues. So you want it to be directly between those nuclei like that.